Today we'll discuss quite a few topics. We start with solvers for Laplace equation. Okay? So I will present how to solve a Laplace equation in a computer. Okay? So what is Laplace equation? I guess every physics student should know, and some engineering students may have forgotten, but let me just remind you. In electrodynamics, we have divergence of electric field is in CGS units 4 pi rho. Okay, rho is charge units. Okay, this is one of the Maxwell's equation. Now, electric field is written as potential, gradient of a potential. So if we substitute here, we'll get Laplacian. That is 4 pi rho. So right hand side I normally write as F, and this equation is called Poisson equation, which we also discussed today. Poisson equation. Okay. Now, if rho is 0, so imagine there is no charge in a region. So there is no charge inside this domain. So rho will be 0 inside the domain, right? There will be a potential applied at the walls, but inside potential is 0. So inside the domain where there is no charge, del square phi is 0. And this equation is called Laplace equation. And it's easy to show that for gravity as well, gravitational potential follows the same equation. When there is no mass, we find this in hydrodynamics for string function. So Laplace equation comes in many places. So does Poisson equation. Okay, but let's focus on Laplace equation. Now in 1D, so this Laplacian, which I'm sure you have come across this. In 1D, this does this 1D. So 1D equation is that. 2D, second derivative with x, the second derivative with y is 0. This is 2D. In 3D, we add third derivative with z. 0. Okay. So I will show you how to solve in 2D. Okay, and this method can be easily generalized to 3D. Okay, so please keep in mind that we are solving this equation in present lecture. So I just recap. So Laplace equation is this. It comes in electrodynamics, hydrodynamics, for string function, magnetostatics. That becomes a vector equation for the vector potential. A is 0 when there is no current. Okay, there is no current, we get that 0. So these are the equations in 1D and 2D and 3D. 1D is trivial. 1D is just a linear function, right? D square phi dx square is 0. So it is just straightforward. Phi is cx plus d. So 1D we don't discuss. We just focus on 2D and 3D. Well, right now we will focus only on 2D. So boundary condition. So for Laplace equation, Poisson equation is basically boundary value problem. Okay, so we need to specify the potential phi on the boundary, and if we do that, then it's called Dirichlet boundary condition. So you specify phi at the boundary. Okay, Dirichlet boundary condition. Second, Neumann boundary condition, where we do not specify phi, but we specify the gradient derivative of phi, normal derivative of phi. So d phi normal. So this is wall. So how does the phi vary when you go in the perpendicular direction? We also written as d phi at dn. The third is mixed boundary condition, where at some walls we specify potential, Dirichlet boundary condition, and some walls we specify the derivative. Okay, so it's a mixed boundary condition. Mixed boundary condition. So right now in my lecture, I will focus only on Dirichlet boundary condition. Neumann boundary condition is a bit more complex, so I will not discuss it right now. So properties of Laplace equation. In electrodynamics, you would have seen this. I'll just state them here. In fact, we use it for computer simulation. So one thing is uniqueness theorem. The solution of Laplace equation is uniquely determined given the boundary condition. So if you specify the boundary condition, that means what is the potential or its derivative along all the points on the boundary, then phi inside is unique. Okay, there's only one phi, not multiple phis. Okay. A second, which is the most important thing, is the average value of the phi over a sphere. So just take a sphere. Okay, average value. So if you just average over phi, that means integral phi d vector r, that equals the value of the function at the center of the sphere. So if we do the average, that is equal to what is the potential at the center of the sphere. All this can be derived, okay, but we are not going to derive it in my course. Third is, this is in 3D. In 2D, it will become a disk. Okay, so average on the disk, like if I just do the integral over all the points on the disk, that equals value of the function in the center of the disk. So now we can use this to, in fact, I'm going to do few slides down the line, use this property. Okay, now let's set it up in 2D. So what do I do right now? We'll make our life simple. We'll keep a Cartesian geometry. Okay, Cartesian geometry. There is a project that some of you will be working on, cylindrical geometry or disk geometry. Okay, but we'll focus right now on a Cartesian geometry. It's simpler, but you can also work on a disk, no problem. So this x-axis and y-axis. Now we make a uniform mesh. That means delta along x is same as delta along y. So, and I specify any point in the grid as with indices. Okay, so this index is right now, the green index is I comma j. So the x coordinate is, x grid point is denoted by I and y along j. So this one is I minus 1j, right, this point, and this point is I plus 1j. So if I traverse along horizontal direction, I'll be increasing I. If I traverse along the vertical direction, I'll be increasing j. Okay, if I go up. Okay, so this is j minus 1 and j plus 1. Okay, so this is just straightforward. In fact, we did this in for finite difference scheme before. So it's the same scheme. Now, so what is the Laplacian for this? At I comma j, at that point, my second derivative with relative to x will be, I apply the central difference scheme. Okay, so I plus 1 comma j minus 2 phi I comma j plus phi I minus 1 comma j by h squared. Okay, so this is the central difference scheme. Now, same thing for y, except that along y it will be varying, j will be varying, j plus 1 and j minus 1 and j. Okay, so now you can sum it up. So Laplacian is sum of these two equal to 0. So if you sum it up, I'll get this equation, right? X1 and Y1. So we rewrite this as pull out phi I comma j. Okay, in this. So 2 and 2 makes it 4. So this goes to the left hand side and this whole thing goes to the right hand side. So I get 1/4. So phi I comma j is 1/4 phi at 4 neighbors. So potential here, okay, you can see my cursor. Potential here is average of phi's at the 4 neighboring points. In fact, this same as the property 3, right? Where I said potential in the center of a disk equals value of the potential at, average of the potential over the disk. Here I discretize it, so the average will be at the 4 nearest neighbors. Okay, so this just comes from the discrete property, discretization of the equation. Okay, so I can write equation for this. So Laplacian phi, Laplacian phi equal to 0 if you look at that equation, so I had, so phi I comma j equal to, it was function of I minus 1j, I plus 1j, and so on, right? So we can write this in terms of matrix. Okay, so actually we should look at this equation. This equation, I'm going to write this as the matrix, this equation. Okay, so here I put all the unknowns, phi 0, 1, like that. By the way, please keep in mind that boundary condition is specified. So this values at the edges are given to you. So they are not variables. So don't solve for them. You solve for phi inside the grid, all the grid points. Okay, so I don't start with phi 0, 0. I start with phi 0, 1, which is, if I start phi 0 will be 0, 0 is here. So this is 0, 1, first grid point, 0, 1. Then 0, 2, like this. Then I go to 1, 1, 1, 2, like that. Okay, so I make this. So these are unknowns. So phi 0, 1. So I make a vector, and inside the A is a matrix. Okay, so A matrix will be, so equation for phi 0, 1 will be what? Okay, so phi 0, 1 will involve phi 0, 0, phi 0, 2, and phi 1, 1. And this point will not be there, okay, because that point is outside the domain. That is basically 0. So we will basically get this matrix A, which is basically 1 and minus 4. Okay, so that's what we'll get. So this is called banded matrix. In fact, since only the neighbors are there in the equation, this will be banded matrix. 4, minus 4, 1, 1. And at some point, there will be 1, 1 here for J. Anyway, so I'm not focusing on this method. It's called direct method. And it's a matrix equation which can be solved. Well, I will do it towards the end of this lecture, today's lecture, how to solve these matrices. Okay. In Laplace equation, I'm not recommending this method for your course. Okay. We'll do indirect or iterative method. We'll do iterative method. Okay. But we should know how to set it up. Okay. So this is a matrix equation and we can solve for this. Inside is only numbers 1, minus 4, 1. Okay. So we should be able to solve it.